On to step 3. Now we're going to prove that mu star is additive on A mu. And then we had an argument for why that implies that it's countably additive on A mu. So we are proving finite additivity of mu star on A mu. So consider any two sets in A mu that are disjoint. Then finite additivity says that mu star of B union C equals mu star B union mu star C. So actually, finite additivity is not just about two sets, it's about any finite collection of pairwise disjoint sets. But it's sufficient to work with just two sets because we have proven already that A mu is an algebra of sets. And that's all you need to let the sort of induction work for going from two sets to any finite number of sets and get finite additivity. So I guess that is one way in which the step 3 relies on step 2, is that since we already know A mu is an algebra of sets thanks to step 2, in step 3 we only need to show that mu star is additive on disjoint union of two sets rather than an arbitrary finite number. And by the way, we already have one inequality of this equality that we're trying to prove. So we already have this inequality, right? That's due to the subadditivity of mu star. So now that I've pointed that out, here's another use of lemma 154. So we've used that 3 times so far in proving the amazing extension theorem. I just noticed a horrible typo here. This is total nonsense. To try to union two real numbers. Okay, so we want this inequality. This is the one we don't have. We want this inequality here. Let me highlight the goal here. Now on the different sides here we have these outer measures. They're infima of certain sets, right? Each one is like infimum of the collection of approximations from above or whatever. So as we have seen several times, it is helpful proving inequalities with infima like this. Sometimes it's nice to have an epsilon, an arbitrary epsilon, and then try to prove your inequality with your arbitrary epsilon. So kind of like, you know, add or subtract epsilon to one side, and then show that for that arbitrary epsilon, with that arbitrary epsilon added or subtracted to one side, you have your inequality. Then you have your inequality without the epsilon as well. Okay, so now that I have an epsilon in hand, I'm going to use the mu measurability of B and C. So since B and C are in A mu, there are, let me call them A, B, and AC again, in the original algebra of sets, such that outer measure AB, symmetric difference B, and outer measure AC, symmetric difference C, are as small as I want. So I can put any positive number here that I want. How about epsilon over 2? And we'll see where that goes. Okay, so I'm trying to prove this inequality, right? Somehow, so the ultimate goal here was to prove mu star is finitely additive. That's the goal of step 3. Finitely additive on A mu. Somehow this is going to use the finite additivity of something, mu, right? Like we know mu is additive, even countably additive, on A. Somehow that fact, the fact that mu star was built out of something additive, that's somehow going to give us additivity, and that's somehow going to give us this other inequality that we don't always have. So how do we bring the additivity of mu into the picture here? Well, mu doesn't operate on things like b and c, right? Mu operates on things in our algebra of sets, like AB and AC. So if I want to bring the additivity of mu into the picture, then somehow I need to work with this, right? I kind of want, let me put a big question mark here, this is kind of the idea, right? But even this doesn't really work. Even though mu applies to these things, since they're in the algebra of sets, A, this doesn't quite work because AB and AC are not disjoint sets necessarily. I mean, B and C are disjoint, but AB and AC, we don't know about that. So that's one problem. But still, we'll be able to deal with that problem, and you'll see. But still, we'd like to sort of bring AB union AC into the picture. So a lot of the argument that you're about to see involves kind of working with these things that we're trying to work with and replacing B by AB, replacing C by AC, and replacing B union C by AB union AC. And with each replacement, tracking what cost of epsilon that we have to pay for making that replacement. So let's start with focusing on mu star B union C. So we've got mu star B union C, and then we've also got something that we think is superior, or will help us more in this proof, which is mu star AB union AC, right? Even though we cannot directly apply additivity to this since these are not necessarily disjoint, we'll still have a way to deal with that. So we still want this somehow. Okay, so what's the cost of, in the desired inequality, replacing this by this? So what we want to know is the distance between these, right? How much do they really differ by? Well, that's something that is controlled by the outer measure of the symmetric difference. Like this. Right? This was one of our earlier things. It was here, actually. So we had this one, which required already knowing you had something additive. We can't use this since we're trying to prove our mu star is additive. But we do have this. Mu star always has this inequality. So we're now using lemma 155 part 1, which tells us, the distance between the two mu stars, these two numbers, is controlled by mu star of the symmetric difference. All right, and let me position this better. Now, that's a really good start, but again, I want to... oh, sorry, actually, no, this is perfect. I'm trying to... ultimately, in the inequality that I'm working with, I'm trying to replace mu star B union C by mu star of this thing. But I'd like to see a good reason for why this should be small. Now, this we've encountered before, right? A union, symmetric difference, a union, where we know things about the individual symmetric differences. So we encountered this back in step 2, right? And then we observed that we have this inclusion, just an inclusion of sets. So this is the inclusion that I'm talking about. If you take union, symmetric difference union, then that's included in symmetric difference union symmetric difference. And so due to the monotonicity of the outer measure, this inclusion turns into an inequality. So I get an inequality here. the outer measure there. So what I'm using there is this one again. All right, and now I'm getting things down to these symmetric differences, these individual symmetric differences that I know something about. Oops. Now I can use the countable or even finite subadditivity of mu star. And get an inequality, turn this into a sum, and then we've got these individually less than epsilon over 2, so this is sum of them is less than epsilon. Great. So now I'm seeing exactly the cost of replacing outer measure B union C with outer measure AB union AC. And in fact, this one I don't have to view as an outer measure, right? Because remember, back in the original theorem, where is it? Here. Back in the amazing extension theorem, we've already proven part 1, where we know that mu star extends mu. So we know that if you're applying outer measure to things that are in the original algebra of sets, that's just the same as applying mu itself. Okay, so back here, I don't need this star here. I don't need this star because this is something that's in my algebra of sets, A. Cool, so let me write down what aspect of my goal I've sort of got here, given the estimate that I just made. So remember, this is my goal. So what I've got so far is that mu star of B union C is, well, what I'm saying here is that it's no more than epsilon away from this number, mu of AB union AC. So that means it's inside the window of real numbers, this minus epsilon to this plus epsilon, right? So then it's greater than this minus epsilon. That's what we have proven. And let me just put in a reminder of what the goal is, so that once this part goes off screen, it's brought back in. All right. So let's log that away. We have this now, and we're still trying to get this. And we think that we can work with mu of AB union AC. But remember, we mentioned a problem earlier that AB and AC are not necessarily disjoint, right? We know B and C are disjoint, but AB and AC, we don't know. And that's a problem for applying the additivity of mu, right? But, I mean, AB is supposed to be like an approximation of B, right? And AC is supposed to be an approximation of C. So if B and C are disjoint, then I would expect AB and AC to be not so far away from being disjoint. I don't know if that makes sense. If AB is like a set that's similar or close to B, and AC is similar or close to C, then you might expect that their intersection is going to be similar or close to the intersection of B with C, which is empty. So this intersection might be close to empty. Now, when I talk about sets being close to each other, really I mean in the sense of outer measure here, which is the sense in which we're measuring sizes of sets here. So maybe even though this is not 0, maybe we can still, even though this is not the empty set, so its outer measure is not 0, maybe its outer measure is still under control. If it is, it'll be under control due to the fact that mu star of B and mu star of AB are very close together, and mu star of C, mu star of AC are very close together. Okay, so here's the official set theoretic way of describing how small AB intersect AC is in terms of knowing about these individual symmetric differences. Actually, let me write them in this order since I've been doing that for some reason. So this is not something that's just generally true for any old sets. This is something that works because B intersect C is empty. So let's do a quick sort of schematic proof. If X is in there, can we prove it's in there? Knowing that B intersect C is empty. Well, if B intersect C is empty, then any given X you have is either going to be not in B or it's going to be not in C, right? So there's this case split that you have for any given X. Then if X is not in B and it's in this intersection, then it's in there and not in B, right? And if it's not in C and it's in this intersection, then it's in there and not in C. So here this places it in this symmetric difference, this places it in this symmetric difference. So we are seeing here that while AB intersect AC is not necessarily empty, it still has to have small outer measure, right? So let me just be lazy here. We have this. And I think you know how it goes. We're now just repeating this argument here again, right? Let me just grab this. Using the countable and even just the finite subadditivity of mu star. So how does that actually help us? Well, remember we had this, right? We have this and we're trying to prove this. So we have this, we've got mu of AB union AC, and our initial hope maybe was to use the additivity of mu, but AB and AC are not necessarily disjoint. Still, we can turn it into something, we can turn this union into a disjoint union if we just rip out the intersection, right? So let's just work with this mu of AB union AC. And let's see if we can get that to be something that's like mu of AB and mu of AC individually at the cost of maybe an epsilon. We think that this is the epsilon that will show up. So mu of AB union AC is, now let me write it as a union of disjoint sets. So I'll just rip out the intersection, like this, lots of parentheses. Then I'll rip out the intersection from this one, and then I'll union in the intersection again. And I see the typo there. All right, finally we can use the additivity of mu. So everything here is in the algebra of sets, right? Is in the original A, algebra of sets, and mu is additive, and these are disjoint. So finally, we have not an inequality, but an actual equality, which is what we need. Of course, we always had this, right? But that's not going to help us, right? We're actually trying to get this, because we're working on the right-hand side here. We're trying to show that this is greater than or equal to, and then replace it by something else with another epsilon. So it's very important that we got this equality here, or at least that we got this. Okay, so there we go. So we've got mu of AB, delete the intersection, plus mu of AC, delete the intersection, plus mu of the intersection. And let's do some algebra. So again, using the additivity of mu. Mu of AB, delete this intersection, is mu of AB minus mu of this intersection. So it looks like we get some cancellation there. But another term is going to show up. So this is mu of AC minus mu of the intersection. And then plus mu of the intersection. Okay, so we get some cancellation here, but there's still a mu of the intersection left over. Okay, maybe if we were using a different textbook, it would have been a lemma or a proposition or something early on that whenever you have an additive function, then when you apply it to a union, even if it's not a disjoint union, you can write it as mu of one plus mu of the other minus mu of the intersection. So this is just a general property of additive functions. But I kind of have to do it out here since we never actually established that on its own. Okay, and now we benefit from knowing that mu star of this intersection is not so big, right? By the way, mu star of this intersection is the same as mu. I guess I should replace it by mu star before I apply that property. So how about I just stick a star here? So I'm allowed to stick a star here. That's because we already did part 1 of the amazing extension theorem, which tells us that mu star is an extension of mu. Okay, now I got greater than or equal to, since this is being subtracted, this inequality flips around, the inequality that my face is covering. I have greater than mu star of the intersection is greater than or equal to negative mu star of the intersection is greater than or equal to negative epsilon. So I have that. Okay, so you see what I was doing here in this line. I was really figuring out what's the cost, what's my epsilon cost for replacing mu of AB union AC by mu of AB plus mu of AC. And the cost is 1 epsilon. All right, so we now can update what we have. All right, I'm copying that yellow line down here so that I can get everything on the same screen. Okay, so given what we just proved, I'm going to update this yellow line in a second. So now we have mu star B union C. We already had it's greater than mu AB union mu AC minus epsilon, and now we've improved our approximation here. I guess this was a strict greater than, not that it matters. But whatever. Okay, so here I've got greater than mu AB plus mu AC minus another epsilon. And there was already a minus epsilon, so now it's minus 2 epsilon. So my original thing that I had down here, I can update. Now I've split these up, and I've paid another epsilon. Okay, and remember still that this is ultimately what we want. I copied that typo over. Here I am unioning real numbers again. All right. So what next? Well, can I replace mu of AB maybe by a mu star B? Can I replace mu of AC by a mu star C? And if I do that, what is the cost? So it sounds like I need to know about the distance between mu AB and mu star B, and I need to know about the distance between mu AC and mu star C. And it's harmless to put a star there, right? So I can just stick a star right here, because we already proved part 1 of the amazing extension theorem, and we know that mu star is an extension of mu, so it agrees with mu when you apply it to things in the original algebra of sets. Okay, and now when I'm measuring the difference, mu star AB and mu star B, that's going to be no more than mu star of the outer measure. So the outer measure controls or estimates, looks like I turned this into a C here, turned the C into a B, okay. And this was, what was it, epsilon over 2, I think. So here we're using this one twice. When you take the measure of a symmetric difference, be it the outer measure in this kind of crappy context, or the ordinary old measure in this context, the measure of a symmetric difference gives you an estimate on how far apart the measures of the individual sets can be. All right, so that means mu of AC is in an epsilon over 2 window centered at mu star C, right? And mu of AB is in an epsilon over 2 window centered at mu star B. So starting with what we have here, we have this. Then mu of AB is inside that epsilon over 2 radius window, right? Centered at mu star B. So mu of AB is greater than mu star B minus epsilon over 2, and mu of AC is greater than mu star C minus epsilon over 2. And I pay an epsilon over 2 for each replacement here, and so overall I've paid another epsilon. And I have a 3 epsilon here. Okay, but look, I've reached my goal, right? Except there's a plus epsilon, or minus 3 epsilon, but epsilon is arbitrary. So since for all epsilon greater than 0, this is greater than that minus 3 epsilon, since epsilon is arbitrary, we have this with a non-strict inequality, of course. And so mu star is finitely additive. Remember, this inequality was the one that we didn't have from the very beginning of step 3. to get we already had this inequality from subadditivity. We needed this one. We've now proven that mu star is finitely additive on a mu, not just on random sets. You can apply mu star to random sets, but on a mu, it's finitely additive. And that's step 3. And in fact, we get for free now, thanks to our previous work, not really for free, that mu star is countably additive on a mu. That's because since mu star is now known to be finitely additive, we know that mu star on a mu sits in this white area rather than this green area. It satisfies these hypotheses here, so we can apply proposition 139 part 3. And having countable subadditivity, which we do, thanks to lemma 154, is sufficient for having countable additivity. And I think I already put the red check marks for using that. So we now know that mu star is countably additive on a mu.